Good evening, everyone. I hope all of you are doing well and are safe. Today, we have the second talk in our series of webinars, the Elementary Lecture Series, where we invite eminent chemists from around the world to introduce the current frontiers of research in chemistry to undergraduate and school students. Today, we have on board Professor E.D. Jemmis from the Indian Institute of Science, Bangalore, who will speak about elementary questions which arose in his UG days. We expect the talk to run for about 60 minutes, following which we will have a 15 to 20-minute session where Professor Jemmis will answer questions from the audience. So if you have any questions, you can just type them in the Q&A box either during the lecture or just after it. Professor Jemmis obtained his BSc from Kerala and Calicut universities and MSc from IIT Kanpur. In 1973, he joined Princeton University under the supervision of Professors Paul von Reichschleider and John Pople, and was awarded his PhD in 1978. He did his postdoctoral studies at Cornell University with Professor Roald Hoffman. In 1980, he joined the School of Chemistry, University of Hyderabad, where he went on to become the dean in 2002. Professor Jemmis was a visiting fellow at the Australian National University, Canberra, and a visiting professor at the Centre for Computational Quantum Chemistry of the University of Georgia, Athens. He is an honorary professor at JNCSR and adjunct professor at ICTS TIFR. In 2005, he joined the Inorganic and Physical Chemistry Department at IISc Bangalore. In 2008, he became the founding director of ISAT Thiruvananthapuram. He currently holds the Year of Science Chair Fellow Professorship of SERBTST at IISc. He is a fellow of the Indian Academy of Sciences and the Academy of Sciences for the Developing World. He is also the recipient of the Shanti Swarup Bhatnagar Prize awarded by the CSIR and the J.C. Bose National Fellowship of the DST. In 2014, he received the Padma Shri Award from the Government of India in the category of Science and Engineering. So without further ado, I would like to hand it over to Professor Jemmis so that he can go on and begin his lecture.
Good afternoon. I presume that you can hear me. Let me begin by thanking my friends at Pravega for giving this opportunity to talk to you all. Elementary is the program under which these talks are arranged, and I have selected to give this title Elementary Questions. And elementary, of course, means many things to many people. Before I begin, let me thank my colleagues. Whatever I have done and whatever I speak are the results of different groups of these students over the last 40 years. The current batch is what you see here. This is the fact of life. Without students, most professors cannot do anything. Of course, there are rare mathematicians like Harish Chandra who never had any co-workers, but those are really, really rare. Now, Elementary has also selected an icon, and most of you will recognize this particular icon. Sherlock Holmes is supposed to have said about the solved problems as elementary to everybody around, but if we search for it, we may not find it. It may be there in the movies, perhaps. But it's a very interesting take on elementary. And if you look at the term elementary, and I thought I would look at the dictionary, and one of them gave three meanings. And it's actually elementary. One doesn't really have to look at it, right? It is too elementary. But these elementary takes different meanings when you talk to different people. It is elementary in a different sense as we go further. But I said elementary questions. When things are elementary, there shouldn't be questions, right? When I say things are elementary, things that we used to know even as kids and nursery rhymes of the kind that that has taken a different meaning. When one begins in the nursery, yes, it is a nursery rhyme. When one is going to complete the school, it takes still different meanings. But these are times when, I'm talking about late 50s, and these are times when there was no internet, there was no cell phone, there was no Facebook, of course, or WhatsApp or anything. And when one is leaving the 10th class, all that you would have in your hand to write something, to give it to somebody, is what is called autographs. And you get these autograph books where somebody or other might write some innocuous, unquestionable truths like this. Now, there are unquestionable truths, yes, especially as the last part one can say, but the rose is red. And yes, rose is red, roses are red, one can say. But immediately you can question this, right? Roses are red? No, not really. You have all kinds of colors, right? So even these unquestionable statements which are understood in an elementary way are not so simple. In fact, it becomes even more complex. In one rose itself, we can have so many colors, right? Why are these so many colors? It's a question to ask. In fact, one can even say, is the red rose really red? Depends. Where do you keep it? In the dark, of course, it is black. Everything is black. But if you have only monochromatic light, then it can't be red. Now, let us assume that we have bright daylight and it is red. How do you know it is red? We can say we see it. What do you mean by seeing it? How do you see it? What happens in the process of seeing? All these are questions for which answers are available. Not to the not to the last point. One would go back to the retina and the change of the cis and trans isomerization, and then the electrical signal that goes out and the neuron firing. And even then, how do you know it is red? The neuron is fired at last bit, right? You think it is red because you feel it is red, or you have this larger neural network inside telling you that it is red. In fact, if you go to the physics, chemistry, biology, engineering of seeing, you get to points where you don't really know even about this simple, taken for granted nursery rhyme. And finally, it all depends. Even the questions that we are asking is a result of all these processes of chemistry, physics, and biology, right? Elementary processes, I said. Elementary processes involving some elements and some elementary particles. Not even elements, maybe an electron moving, right? So questions, even the simplest one that we started with is not as elementary. And of course, I don't want to go to sky is blue and honey is sweet and all are terrible questions to say elementary. Most of the answers we have, not all, in these simple questions, elementary questions. So when I say all questions are elementary, not quite. But whether questions are elementary or otherwise, there is one thing that one has to realize. Ability to ask questions decides the success of a nation. It is not as though only the genius will ask questions. The habit of asking questions can be trained easily. But the truth is, it need not even be trained. If you have siblings around who are 2, 3, 4, 5 years, you keep listening and then you see what they're asking. They're asking questions all the time, and most of the time we get annoyed and say, oh, enough is enough. But this should not happen. The habit of questioning should continue. unfortunately, often somewhere it is lost, maybe in the school, maybe later, and that shouldn't be. It is because questions that one can ask early on tend to be more general than the questions that we ask later. Somebody who is finishing PhD in high energy physics or pluripotent stem cells or whatever else will only ask questions that are relevant and that are applicable from what he or she has learned. But if you ask someone who is just beginning the PhD program, a graduate study just beginning, uh, at least if he's starting in biology or chemistry or physics, the questions could be general in that area. But someone who is starting out as a UG student, especially where there is more flexibility, one would have the feeling, okay, if I am starting out as a UG student in humanities and social sciences, I'm still open. Fine arts and performing arts and communication and economics and literature are all open for him or her. If one is starting in a BSc program where you're already compartmentalized, even there you would say, okay, you have BSc with mathematics, physics, and statistics, and you still have questions that will involve all these topics. But it's even better if you go to high school. Their questions could be really general. And it is nothing surprising because you don't really specialize at that stage. It's almost like going backwards in time. Why I said backwards in time? When civilization started, when human civilization began, everybody did everything. Aristotle and Newton, even Indian philosophers, any name you take, Aryabhata, they all did everything in some sense. Whatever, caught their fancy, they went on to study. But then, as knowledge increased, specializations became inevitable. And yet, if you go back to important discoveries, it's always through multiple disciplines coming together. And in that sense, when one is young, it's almost like a civilizational beginning, because what is already known hasn't influenced us because we don't know much. And even the philosophy of such knowledge and its influence has not influenced us, right? So we tend to ask general questions. So it is important to ask questions right from the beginning. In fact, when I meet students, I tell them to have a book, and I say a book because formats keep changing. Whatever I have saved in 25 years or 40 years on different media, I can't use now, and I'm not so good at keeping and changing and transferring data. So I would say a notebook, and write questions that you ask on anything. And I know several students who have finished 4 years and found that there are at least 4 or 5 pages of important questions. Some of the questions become almost trivial because the answer is known or answer can be found so easily. But it is important to ask questions. And I come to an elementary question. I put the hyphen about an element actually. About an element, and this question was asked when I was a first year BSc student, and in a very inelegant way this question was asked, but nevertheless it was a question that was asked to a teacher, and I had a really good teacher who was teaching about carbon allotropes and the connection between compounds of carbon and allotropes of carbon. These days we know about graphene, we know about things didn't exist at that time. This was 1968, but nevertheless we had this beautiful explanation that you start with methane. It has a tetrahedral carbon. Van Hoff and Lebel has started this idea, and you generate structure with the carbon connected to 4 carbon connected to a carbon, and then you can just develop diamond. Such a beautiful relationship when it is talked. Similarly, you can go from benzene to naphthalene to anthracene to graphite. Those days we didn't even worry about graphene. And you see the names and people here. In fact, C60 even could be explained by sp2 hybridization. Slight strain. I see +2 books having these things now. The first of it came in 1984. In 68, nobody thought of this, right? So this known part of carbon chemistry was explained, and I happened to ask this teacher. This was Professor Shankara Iyer at University College in Trivandrum. I happened to ask him. Actually, he was walking out of the class. I said, "Anything like this for boron?" And he turned back and we discussed this. Anything like that for boron? Just as carbon. And this was a simple, innocuous question. And we looked around. There was this new textbook at that time. This had just come out in 66. The Advanced Inorganic Chemistry textbook. It was still called at that time Advanced Inorganic Chemistry textbook by Cotton and Wilkinson. Didn't have it. So we didn't quite know what the structure was of allotropes of boron itself. Forget about the connection between compounds of boron and allotropes of boron. I went on to IIT Kanpur for a master's, and I asked the same question. It was not clear. They couldn't find any literature answer, and I kept on with it. I decided that I will look at these things on my own. In PhD program at the chemistry department in Princeton, we had to submit 2 research proposals independent of the PhD thesis work for defense, and I was trying to write about boron and carbohydrates and compounds like that. Whatever it is, I was still pushing hard to find an answer. Didn't leave it, but I couldn't find an answer till 20 years ago. That means the first 30 years I didn't have any idea. I didn't leave it. But of course, you can't search for an answer and do nothing else. Then you would not even get a job. So I did other things. And other things, while doing other things, you kind of generate your own ideas and philosophy of doing things. So these are not as important, but I just want to say that one should not be stuck with one, unsurmountable problem and spend the whole life. You have to see various things that one can do, not just one thing. I will skip these, but these are different kinds of things that I do in research. But I come back to this one question that bothered me for 30 years. And I try to formulate this question better in a way that one can understand better. This formulation, I initially thought, yes, sp2 and sp3 and sp hybridizations and Huckel-Farrand +2 rule helped us to go from methane to diamond and benzene to graphite. Is there something similar, or are these the right questions for the purpose? Is it possible to make this connection? So these questions is elementary in some sense because I'm talking about elements, but they are not very elementary because the answers are not there. But if you look at this logo once again, you see in the magnifying glass almost a benzene. So I took this benzene out, and there is a polyhedral borane which is having icosahedral symmetry. In the 2 dimensions, it looks similar to this. So if you consider benzene and its equivalent, B12H12 2-, this is a well-known molecule which was already known in 68. An icosahedral borane dianion. A very stable system, almost like benzene. Benzene is aromatic, stable. You all know that, right? 6 pi electrons and so on. This is -2 charge species, very stable. In fact, you could, of course, make a replacement of 2 boron atoms and make it with carbon, so you can get it as C2 beta H12, which is neutral. Extremely stable system. And I was thinking that, okay, just as benzene has gone to graphite, can we take B12H12 minus and go to different allotropes? Now, this kind of a diagram I couldn't even think of in 68 or even 78. I had difficulty making this diagram because I hadn't understood the structure of alpha boron, which was easy to explain. This is there in textbooks now, but beta-rhombohedral boron or tau boron, they are far more difficult. And I probably may not reach there in today's talk because you have to put benzene, the three-dimensional equivalent of benzene, the borane chemistry equivalent B12, H12 minus, we have to put them together and it becomes larger and larger and unit cell becomes large and so on. But there is another equivalent allotrope that is more recent, which I can explain even to +2 students. So I will explain that in greater detail and I might come to these rules a little. I probably will not reach to the structure of beta-rhombohedral boron, which is the thermodynamically most stable allotrope. But all this I am saying this not because this is the only thing I have done, but because this is the only thing I have asked so early and I kept it. I didn't leave it and I reached to some partial answers. These answers keep coming now, last 20 years, and not just me, many others. So it is necessary to keep asking questions. There is no excuse for not doing it. If one wants to generate ideas, it's a habit that should grow early. Now, this B12H12, if I were to remove all the 12 hydrogens, suddenly one realizes that the whole thing becomes flat. This is now known experimentally. That is, if you remove the 12 hydrogens, if you only have 12 boron atoms, this will be flat. Now, I didn't even think about two things behind here, right? Because there are other kinds of structures as well. It's not just that if you have only boron clusters, it will be flat. You know, if you have 40 boron atoms, it is almost like a C60, like a fullerene. It's called borospherene. 40 atoms. It has actually 6 large holes. So this is something very interesting. We are working on this. Many people are working on this, but I won't get to any of these things. In other words, allotropes of boron keep increasing. Like in carbon, we had an allotrope discovered in 1984, that is C60. Now, how to put this B12 and make something like a graphene? It's almost like graphene, but you know, there are some extra holes, right? So we will concentrate on this path alone for the moment, and if we have time, we will try to move further. Well, this is just to show the shape of things that are there, which we will not really worry about. You know, we start with the B12 and you put them together and you essentially get to complex structures which are the hallmark of beta-rhombohedral boron and tau boron. And there are very, very unusual aspects of this problem that evolved over the years. So it is not as though I would talk about all of this, but I gave this picture as well as the next one more to tell you that yes, there is a lot more that we need to know still. What do you all know? What do we all know? I mean, we know that Lipscomb got a Nobel Prize for working on boranes. We also know that H.C. Brown got a Nobel Prize for working on hydroboration, right? Hydroboration, I'm sure you have seen before. William Lipscomb had made these polyhedral boranes and several bonding ideas in this, studied their structure and so on. We of course can go back to methyl cation and see that yes, there is an equivalent which is BH3. We know that if it is CH4, we could have an equivalent BH4 minus. These are all isoelectronic comparisons which we can keep doing. If it is C2H6, well, if you don't have enough hydrogen, I mean enough electrons, like 2 electrons are less, so we have bridging hydrogens. I'm sure you have seen the explanations of this, right? The bent bond or bridge structures. It's almost like you have 2 protons interacting with an ethylene dianion, one interacts with one plus combination, so to speak, interacts with the ethylene pi bond, and the other one reacts with the sigma bond, and so on. Right, this much but a lot more new chemistry is there, so that it is worth worrying about boron. We don't anticipate boron-boron double bond, nor boron-boron triple bond, but both are known. I mean, not very long ago, but more recent years. What is more interesting is that this triple bonded species will react with carbon monoxide, and you get something like this. The triple bond was between these two boron atoms. Now you have a totally different species. So a lot more chemistry is happening. So I would skip all this just to say that yes, it is worth worrying about boron because there are lots of things happening in this. So let's just come back to this idea. We go from B12, remove all the hydrogens, we get this flat one. If you now want to get a structure which is like graphene, it's something like this, all triangles, right? I make an infinite 2D structure like this. It's almost like graphene, right? I say almost like graphene. It's almost like adding one more atom in the middle of all these hexagons, right? So it's almost like graphene, but it is not quite that. To really keep it that way, I have added blue color here to say that yes, there is this added atom, and there has been a lot of theoretical studies. You study this to see what is the binding energy per atom. In other words, if you have to separate each atom from here, the energy required is about 6 electron volt, right, for each atom. So it is binding energy per atom 6 electron volt. But one finds that if you allow to relax these borons, it does something unusual. One line of it goes up, the other line goes down. So there is a striation. It's not flat, and that makes it even better. The binding energy is higher. But something more interesting happens when you select to remove some atoms here. If you remove some atoms here, the binding energy becomes even better, right? In fact, the best is if you remove 1 out of 9 boron atoms. Right? These are computational work, not done by me first, right? It is there in the literature. A lot of people have worked on it, and we were wanting to work on this. We started working on this, and I had a student, Dr. Prasad. Prasad nearly completed PhD in 2008, and we had started working on this, and then he went on a postdoc, and finally he became a faculty member at IIT Kanpur. I went to start ISET Trivandrum, ISET Thiruvananthapuram, and the next 5 years I couldn't do much. I had to wait to come back and get another student, a PhD student who did MSc in IIT Kanpur, to join in 2013. And I can tell you, 5 years in a field like this, it's like an eternity. You cannot go away and come back. But I did. Looked at what all things happened in that 5 years. Many things happened computationally in this 5 years. People have computed all kinds of flat structures. I give here all kinds of notations because each group which studied this used a particular method of density functional theory, and you can't compare these numbers because each one used a different method, and so different calculations couldn't be compared. So we decided that we will do all of these things again, and with one method so that we can compare. I have made the relative energies here. It is milli-electron volt, so that these numbers are large instead of very small numbers that we have seen. And it is relative energies. We had already seen that 1/9 whole density, that is 1 out of 9 atoms missing, would be the most stable one. So 0.0 corresponds to the most stable arrangement. If we had no holes at all, that means no atoms were removed, then this is much higher, right? Even if it is even if it is not flat, even if it is striated, it is still higher. If you increase the number of holes beyond 1, 2/15 or 1/5, that also is not quite favorable. And you can do this, I just show the structures that are used. It's not as important. And one can say, why is it this way? Why 1/9 whole density? In other words, 1 out of 9 has to be missing, not more, not less, to have the maximum binding energy. Well, it was a theoretician's curiosity until 2015, but between 2015 and 2020, there was an explosion. Now what almost it is increasing very quickly of experimental attempts making graphene. Which is of course now christened as borophene, right? Which is similar to graphene in many ways, but not very similar in many other ways. But they made it on a metal surface. Most of them on a silver 111 surface get a mono layer of boron atoms. It's essentially a single atom deposition. Difficult experiment. You make a deposition and then you use the scanning tunneling electron microscope to see where the atoms are, then look at the symmetries and see whether there are holes and so on. This set of experiments prompted us to essentially study these on the silver 111 surface. The same layers that we had studied earlier, we study this on the next layer. This is interesting because what we thought as the most stable one with 1/9 hole density suddenly is not the most stable one. The stability of this monolayer on silver 111 surface increases when we increases the number of holes. And of course, it comes to a saturation. I have done this more, but that doesn't improve things much. It becomes worse. So there is somewhere here, that it looks as though the stability is better, and that also is a problem. Why is it? How do we understand this? Because these computations can be done because there are softwares now, large number of different kinds of softwares, and the theory is well understood as to how the software actually works. It is not so difficult. People have made different ways of computing, but it is necessary to have some kind of a model to understand this so that we can go further. Now, this understanding, is important because, what are we saying? We are saying that we have the result, we have the experiment, we have the computations, right? Even the experiment shows that yes, there has to be probably more holes here than we anticipate, right? So, when we have the experiment and the computation saying something, we still need to understand because an insight that we gain will lead to further design of experiments. A number without understanding may not do that because you have to do again another calculation. But things have changed. Charles Coulson was a quantum chemist who said this in the 70s. Now we say, give us insight and numbers. We can get good numbers and then let us understand it right as well. There was a mathematician, Wegener, used to say, if he has an algorithm that works, he said, yes, it's nice to know that the computer understands the problem, but I would like to understand it too. So what is this understanding that people talk about? It is, in a totally different context, this is the kind of understanding. You could make all the measurements and you have a great design, but if your kernel happened to be like this, you're putting a big question mark on a poor being. So it is necessary to have reasonably good quantitative approaches that has a basis starting from a qualitative understanding. Now let us come back to an explanation for what we have said. I start with this benzene, and we were talking about forming graphene and graphite. But if you remove 2 electrons, we have benzene dication. Now you will surprise yourself. Just 3 years ago, there was an X-ray structure of this dication where these hydrogens were replaced by methyl groups. So this will be C6 CH3 2 plus. It has this pentagonal pyramidal structure, right? Of course, there is a C4B2H6 neutral one. There is a B6H10 neutral one, and so on. So there is this, connection that we have from carbon to boron still happening, right? If you remove 2 more electrons, you have C6H6 plus 4, that is not known, but B6H6 minus 2 is. But that's not the discussion that I want to lead you to. But I want you to look at this structure here, right? Akimitsu in 2001 found out that the magnesium boride that he had in the lab, this is known from the 50s, a compound is stable. That is superconducting at 40 degree Kelvin, very unusual, right? Just a binary solid. And what is the structure of this binary solid? It is MgB2. The binary solid, it has a structure, this hexagonal network, right? That is like graphene. There is no question, except each carbon is replaced by one B minus, right? Each carbon is replaced by one B minus. So we have a graphene with B minus, and for every two B minus, we have an Mg plus 2. So we have another layer with Mg plus 2. Mg and boron are not of the same size. So we have a boron layer, we have a Mg layer. I said this electron count as -1 and for boron and +2 for Mg. That is just for our electron counting. The actual distribution of electrons are not indicated by this extreme charges. But what is interesting is that this is isoelectronic in some electron counting way to graphene, and very stable and superconducting. Now, one of the ways of understanding our 1/9 hole density is by starting with this. Let us start with magnesium boride, right? MgB2. And if I replace the Mg by a boron, right? I replace an Mg by a boron, so we have B2. It's almost like the picture I had shown you earlier, right? There is the boron that we have in the beginning, and now that the Mg is replaced by boron, boron is the same atom, whether it came from the initial B2 or the boron replacing the Mg, right? So there is no distinction. So we can't have these the two layers that we had. We have only one layer. The boron actually becomes a part of the 2D sheet. It inserts in the middle of the hexagon. So we have a triangular structure. Trianguline, it's a trianguline, obviously. Now, if we just consider an empirical formula which is Mg3b6 instead of Mgb2, we have B3b6. So there's only one problem with this replacement. What is this problem? The problem is that this replacement, right? This replacement brings us one extra electron. One Mg replaced by one boron brings in an extra electron. If we have Mg3b6, excuse me, this is B3b6, we have 3 extra electrons. Now we started with Mgb2, which was isoelectronic to graphene, and suddenly we see that we have 3 extra electrons. How do we get back to this electron count that we thought was ideal, right? One way is that in this B3b6, that is B9 system, remove one boron atom, right? If we remove one boron atom, what happens? If you remove one boron atom, definitely 3 electrons are removed, right? And then we get back to the same electron count as in Mgb2. And when you have 2 plus 6 now instead of 3 plus 6, we have only 8 atoms, right? 1 out of 9 is missing. This, this is a simple enough explanation why 1/9 hole density seems to be ideal for the standalone borophene sheet, right? But we could ask the question, if this is true, if you do not remove it, why is it really going out of flame? Let us assume that if we did not have the holes, it means that we have more electrons than necessary. right? Obviously, the electrons have to go into antibonding bonds. I don't get to the electronic structure of solids here, but you can, in a simple-minded way, assume that yes, in a linear combination of atomic orbital model for band structure evaluations, we could see that antibonding orbitals, antibonding bands are being filled. And if these are filled, what is the way to decrease the antibonding interactions? You can actually pucker the system, right? You have decreased this antibonding interaction, it's less. If anything, you have some bonding interaction coming here. This is what is happening here, right? We have a puckering. So this is a nice explanation, for the buckling of the structure. One can of course ask, how does the metal template suddenly finds that it is better to have greater number of holes? Now, I think even you could answer this question, right? How could this be? How could this be? A metal like silver, whose work function is not very high, it is possible for the metal to stabilize the boron layer by donating electrons to the borophene. But to donate electrons, the borophene needs electrons. The borophene with 1/9 hole density doesn't need any further electrons. But if you can increase the number of holes, certainly the metal can donate electrons, and that would stabilize the layer further. So all experimental structures so far has hole density that is higher than 1/9. The actual hole density is kind of going around in this area, right? Slightly more, slightly less. But if you change the metal, the scenario changes. It depends on how easily the metal could donate. With gold, it is not so easy. You have to find other ways of making a monolayer on gold, almost like getting a metal boron alloy and then reducing the temperature and squeezing out the atoms as slow as possible to form a monolayer. So these are all experiments that is just going on now. It's not anything that is done, and I would not continue a lot more on this, but you see how one innocuous question has got me into something that is complex, something that is known only now. Now let me come to at least the beginning of the next problem. That is, borophene is still much higher in energy compared to beta-rhombohedral boron, right? So I would try to come to now a situation where we begin to understand how to put these icosahedral boranes together. Now, why icosahedral borane? I haven't shown this, but it is easily possible to show that when it comes to boron, icosahedral borane dianion is the most stable of the polyhedral anions. We have BnHn2 minus, and already for polyhedral boron anions, polyhedral borane anions, there has been a rule made by Wade. Our attempt is, just as we have done this for Huckel, going all the way, we would like to do something like this, right? How do we do this? I will skip this. We had shown just a little while ago benzene to pentagonal pyramid to an octahedron. We can do that with a 5-member ring and we get to a trigonal bipyramid. We start with tropylium cation and we get to a pentagonal bipyramid. Corresponding to each of these, we have boranes. Well, it's a little complex picture. You don't have to worry too much about this. I will skip this and get to what is known. What is known is that if it is a polyhedral borane, the Wade's rule says there has to be an electron pair extra. He puts it as n+1 skeletal electron pair rule. In other words, if you have n vertex polyhedra, like 12, we should have n+1 electron pairs. Now, how do we count this? boron has 3 valence electrons. This is not rocket science, even though in the beginning boranes got a boost because people thought that this could be used for rocket fuels. But BH, with 3 valence electrons, and we have a new bond formed BH. So we have removed 1 electron in forming this BH. So we have 2 electrons left on boron. So each boron essentially gives 2 electrons to this. That means an electron pair. So if we are n vertices, we have then n electron pairs coming in. And we should have a -2 charge to have this rule n+1. Now I'm not showing the derivation of this rule. It is not so important, but it is good to know that it is possible to have all these polyhedra, B12 H12 to minus, B11 H11 to minus, B10 H10 to minus, and so on, all the way B5 H5 to minus. And of course, we can remove one vertex and get a nido structure. So these are all known. In fact, the rule for weights for polyhedral boron anion came out in 1971, 3 years after my question to Professor Shankar here. But what is interesting is that this rule is applicable only to polyhedral boranes, one polyhedra. How do we make it to different way of condensing this? And we had to make another rule for it, and we called it as MNO rule because we started with n+1, and that 1 was made into a variable m. So it was n+m initially, but then we also found that when polyhedra connect with another polyhedra through a single atom, it requires an additional electron pair. So we have an m+n+o rule, and it is not very complex. It is simple enough. Let us assume that we have 2 icosahedral boranes, right? But shared or connected through a triangular phase. Now, in doing so, 2 things happen. One is that instead of 12 plus 12, 24, we have 3 atoms less. So we have only 21, 21 boron atoms. That's one. The second is that these ones that are bridging, they do not have any hydrogen atoms, right? So it is B21H18, and we have this rule, right? M plus n plus O. M is the number of polyhedra. We have 2 polyhedra. N is the number of vertices. Should have been 24, but 3 are being shared, so we have 21. And of course, these 2 polyhedra are connected through a phase, so this O parameter is 0. So we should have 23 electron pairs. How many do we have? We have 18. There are 18 hydrogens, so we have 18 BH groups, right? Each BH we know brings in 1 electron pair, right? Because 2 electrons are left, so 18 electron pairs, and 3 borons. Each boron has 3 valence electrons, so we have 9 electrons, 4.5 electron pairs. So we have 22.5 electron pairs. The electron count demands it to be 23. It means that we need to have a -1 charge if this is to be made. Now, this was a risky prediction. We had the general rule. It's a risky prediction, but in 2007, the group of Bernhardt in Germany actually made this. It is actually an anion, B21H18. Interesting chemistry comes out of this. But there was an older molecule. This is B16. Right, B20, because we are sharing 4 atoms instead of 3. So instead of B21, it is B20, right? And there are only 16 hydrogens. So it is B20H16. Now, if you count the number of electrons required here, we have 16 BH and 4 boron atoms. So there is 16 electron pairs, and 4 boron, 4 into 3, 12. That means 6 electron pairs. So it should be 22. Right? And what is obtained here, m equals 2, n is equal to 20, that is 22. So what is required is 22, what is available is 22, so this should be neutral. And this was known for 50 years. Actually, Lipscomb, who got a Nobel Prize for boranes, had made this. But what was strange was that all the molecules that he has made were dianion single polyhedra, and by chance he got this in a reaction, he got an X-ray structure, he published it as a communication and left it. He didn't worry about this chemistry at all, unfortunately. Otherwise, we would have known all of these things much earlier. This was made in 68 or so, right? So some things, happen and it is not followed upon. So it is important to keep your ears and eyes open to what is possible whenever you are doing research. I mean, Lipscomb didn't miss much. He still got a Nobel Prize, but in boron chemistry itself. But these are the truths about research: how we win, how we do not win. This particular rule can be used for explaining many different things, right? Even complex molecules, polyhedra of various kinds put shared by one atom, all kinds of things. In fact, you can have metal borides of various kinds, which can be explained by this. In fact, many experiments were done based on this. We could extend this further. Like we have phenandrine and anthracene isomers in benzenoid aromatics. Similarly, we could have isomers, 3 different isomers for B30H24. And what is amazing is that these are neutral. B12, H12, 2 minus. When it became B21, H18, it was 1 minus. B20, H16, it was neutral. Again, if you have 3 polyhedra shared by a triangular face here, another triangular face there, it becomes neutral. In other words, rules are far more complex when it comes to condensing polyhedra. This is interesting information which can be used in many different ways. What is more interesting is that if you restrict this rule to 2 dimensions, we can get the Huckel current plus 2 pi electron rule back. Now, how do we do this? Let us take hexagonal bipyramid, right? This is a hexagonal bipyramid. We have another hexagonal bipyramid, right? Sharing a vertex, sharing an edge, the ABB bond shared, right? So we have 2 polyhedra. So the value of M is 2. How many vertices we have? See, in this there is 6, 7, 8, and here we have 4, 8 plus 4, 12, again 2 more, 14. So we have a structure with 14 vertices, and 2 of these borons do not have hydrogens, so we have 12 hydrogens, and we count the number of electrons that are required. It is M plus N plus O, 2 polyhedra, 14 vertices. O is 0 because it is not a single atom that is being shared, it's an edge. 2 atoms are shared, so we have 16 electron pairs required. How many do we have? We have 12 BH, right? So we have 12 electron pairs and 2 boron, right? That is 6 electrons, 3 electron pairs. So we have 15 electron pairs. We need 16. That means we need a -2 charge. So if we have to make this, we need to have B14H12 -2, right? This itself is not known, but some transition metal derivatives of this are known, which are so-called isolobal, and I wouldn't worry about that term here now. But let us try to connect it and make it 2-dimensional, right? Let us pull 2 vertices from these. A BH from there is lost, another BH from here is also lost. So this is a hexagonal pyramid. This is another hexagonal pyramid, and we have a connection, right? Now, I haven't introduced this P earlier. See, when we were looking at Wade's rule, it said if you have a vertex missing, then you need to add another 2 electrons, and that parameter is brought in here as well. So this variable P comes in when you have what is called a Nido structure, which comes from Wade's rule itself, nothing added by me. Now, if you do this, let us count again, right? We have 2 vertex left, so we have B12 and H10, because these 2 do not have any hydrogens, and there are 2 vertices missing. So there is a variable P which is 2. So we should have 2 for M 12 for N, 0 for O, but 2 for P. That is 2 missing vertices, which means it is bis nido structure, according to Wade's rule itself there. So we need to have 12, 2, and it's 16 electron pairs. We have how many? 10 BH and 2 boron, right? And that's only 13. So we should have 3 electron pairs. It should be -6 charge, right? This is B12 H10 -6, or it should be C4 B8 H10 -2 if you want to take a carbon equivalent. But this is the situation. Now let us make it really two-dimensional by removing these two also, right? Here the rule is remaining nearly the same, M plus N plus O plus P, but P becomes 4 because instead of 2 more vertices have gone, right? M is 2, now vertices 10 only, right? 6 here, 7, 8, 9, 10, right? So 10 and 4 of these missing vertices. So it's kind of a 4-nido system or to aragno. So 4-nido will say it should still have 16 electron pairs. How many does it have? It has 8 BH and 2 boron, right? This 4 will be B4H4, again B4H4, 2 boron. So 8 BH and 2 boron, we have 8 plus 3, 11 electron pairs, right? The difference is 5. So we need to have 10 charge. Now that is B10 H8 minus 10. Now B10 H8 minus 10. You know, B10 minus 10. Each B minus, if you replace by carbon, we have then C10 H8 neutral, isoelectronic replacement, and C10 H8 is actually naphthalene. But naphthalene, we say, is only 10 pi electrons. What happens to the remaining electrons? You know, we should have 22. Where are the remaining electrons? You know, in naphthalene, Huckel have taken only 5 electrons. We have to add also the remaining sigma electrons as well of the CC bond, because we were always considering a polyhedra, right? BH giving its 2 electrons to the whole system, right? If we add the 11 CC bonds or 22 electrons that can come, suddenly it becomes equal. So if we make this equivalence, you see that there is no change, right? So we, you know, see what is interesting is up to here, these electron counting rules are in textbooks because it is easy enough. I could explain to you, you know, even a +2 student among you would have understood, I presume. But so these are available in textbooks, including the recent one by Anil Elias of IIT Delhi, or the very first one, you know, inorganic chemistry, Meisel and Carr in 2003. But the structure of beta-rhombohedral boron is not there in textbooks because you have to deal with it. You start with B12, you would like to make all of them as B12, so you have structures that are becoming more and more complex. And when it becomes complex, textbook writers would just leave it out. They would write about C60. In fact, a fragment of beta-rhombohedral boron is like C60. It has a B60 surface, exactly like a C60, right? But below each of the 5-membered ring of this C60 equivalent, there is one boron atom because it is a pentagonal pyramid, right? And each of this single boron atom is connected to a B12 icosahedra. So it is almost like a C60, except this C60 has inside that 12 boron atoms below each 5-membered ring, and below each of these 12 boron atoms there is the connecting B12. This is one of the building blocks of beta-rhombohedral boron, and you will see, of course, these follow the electron counts that I just mentioned. It becomes complex, and so textbook writers would not take the trouble. But it enables one to think of many more problems with the structure, because this is an idealized unit cell, but the real structure is very different. It has holes like the 2-dimensional borophene, and that is a topic I will not worry about. A lot more is happening in this. I would stop at this stage. Well, these are pictorial summaries. The important message I would like to ask is that the ability to ask questions is important in every realm of life. As a student, as a researcher, as somebody doing any kind of creative work in life, it is necessary to see right questions, to improve, to change, to understand, to plan in everything. Let me start by thanking my Pravega friends, the department where I work, the computing facility of the institute that helps me, the Department of Science and Technology that funds my research, and all my students. So I thank you for your kind attention. I would like to say that you can ask me any question, but you can also send an email in my address, and it is not so easy to, not so difficult to find my email. Just put my name Jemmis in Google and you get it. My name is simple enough, Jemmis. I would like to encourage you to ask questions now or later. Thank you.
Thank you, sir, for that wonderful talk. We have some questions and some general comments as well. One person thanks you for the insightful talk and the stress on the emphasis of asking questions. Another person is asking how can a question be characterized as elementary or not elementary?
Am I audible?
Yes, sir.
Yeah. Well, questions, of course, are the essence of life. The moment one stops asking questions, then one is almost intellectually dead. But how do you know the question is elementary? In fact, the important point is that any question pushed to limits suddenly becomes not elementary. Like the rose is red, right? Elementary, is the rose red? Yes, of course it is red. Not all roses are red. Some roses could be multicolored. But why is the rose red? Are you sure it is red? How do you know it is red? Elementary question, but you go all the way and people are still worrying about what really is the neural network that is our brain, which makes us feel that there is this red color. What level of firing of the neuron would give you enough impulses in the brain to say that it is red? We do not know. So any question pushed to the limits is an important question. It suddenly becomes not elementary. I don't know if I made sense. Do you have? The one who asked question could key in a message if necessary.
While we wait for his answer to his question, I'll move on to the next questions. This is more related to the talk. So a couple people actually have this question, more than two actually, three people have asked a similar question. Could you please mention why you thought of boron and not silicon, which is supposed to be more similar to carbon as it belongs to the same group? Similarly, another person has asked, does silicon have analogues to graphenes or boron allotropes? How is the bonding controlled in those cases?
All of these are interesting questions. Why did I not ask about silicon? Honestly, I don't know. Probably because the elegant presentation was about main group chemistry, and he was talking about the first row. So in that first year lecture room, maybe I was too. I should have been asking more questions, but I am asking those questions, and many others are asking the questions that you are mentioning. In fact, there is the silicene equivalent of graphene already, and people are also thinking now that one could have borophene layered on silica. So these are exciting areas, and I'm talking about what is happening now. The reason I say this is that we think graphene is a super material. It is a super material, but borophene on a silica surface might even be better for the following many reasons. One, of course, the mechanical properties. We know that graphene is very mechanically very stable, strong, and so on. But borophene is even more so because it is triangulines, not hexagonal sheet. But it has an advantage. If you want to add electrons or remove electrons from graphene, what do? Not easy. You have to either add a nitrogen or add a boron. That's the only way to add and remove electrons from graphene. Or, there is no other way. I mean, or a metal. But in the case of borophene, you can just control the number of holes. 1/9 hole density on an ideal sheet, but the hole density could be varied almost infinitely. And so you have the control to make it N-type or P-type so easily. So there are many such unusual things. You can mix the silica surface as a neutral one for borophene to be stable, but many things are being done. But these are all work of last 4 years, really speaking. And so, graphene took so long to reach here. Borophene has just come, so it might take a while.
One person asks that how difficult is it to establish any theoretical predictions regarding boron chemistry? What is the level of difficulty in synthesis of such compounds as compared to carbon compounds?
Yeah, the stable ones are synthesized. They are the polyhedral borane dianions. But the bare boron clusters are harder to make. The structures that I have mentioned are made by either single atom vapor deposition or by exhaustive oxidations of this boron and tracing out the boron clusters without oxygen atoms. So it is not an easy experiment. That is really the reason why it has taken this long to have the first of these experiments. Right, last 4 years only after so many years of trial. But large number of attempts are going on, and I'm pretty sure that not only in the gas phase, it might be there in the solid phase as well for smaller clusters. See, smaller clusters of the kind that I talked about, whether it is B12 or B14 or B40, they are all available only in the gas phase as it is, characterized on mechanism of photoelectron spectroscopy and comparing to the structures, the experimental spectra. So it is difficult, but it has greater advantages. So it will happen for sure.
Another person asks, what is the electronic basis for the Jemmis rule? Just as Huckel's rule has an electronic basis resting on Huckel molecular orbitals, what is the corresponding basis in borane chemistry?
Yeah, it is the same, except in 3 dimensions. It's like, I was, let me see if I can, is it okay to put one slide back?
Yes, sir, just hold on, I will send it live.
I will just get back to one of these. Is it coming through now, the slide?
Yes, sir. Yes,
okay.
Sir.
See, benzene, yes, Huckel 4n+2 pi electron rule, right? We have 3 stable pi MOs and 6 electrons. Now, I said we have 2 electrons less here in benzene dication, and it has this structure. You can analyze this as a C5H5 2-, that is a cyclopentadienyl anion, interacting with a CH +3, so that the total charge is 2+. Right? Cyclopentadienyl anion also follows the Huckel 4n+2 pi electron rule, except these pi MOs, well, maybe it's easier if I even, teams provide this facility. So let me stop the presentation. I think I could do that from my side itself, right? Yes.
Yes, sir.
Yeah, and I will get to the Well, I hope I can get to the whiteboard, or is it not available? I don't see the whiteboard. Yeah. Is that is there a way that you can make the whiteboard available to me?
No, sir, not from my side.
Okay. Why is the whiteboard missing? Maybe I turn the camera off. Would that help? No. Okay. I see the whiteboard is not there. All right. So let me get back to, yeah. So let us get back to the earlier part. The slide is back.
Yes, sir.
Yeah. So we have the 5 molecular orbitals of cyclopentadienyl anion, and we have the CH groups orbitals. One is an sp hybrid, and then 2 p orbitals. These p orbitals here, a p orbital here, for example, could interact with the pi molecular orbitals. So we have a delocalized pi molecular orbital here, not in 2 dimensions, but in 3 dimensions. And when we come to this, we have a cyclobetadiene, and you have 2 sets of such orbitals. So we could easily see the delocalized nature of these. And of course, one can do the computations and establish the electronic structure basis, right? Like what Wade has done. Something similar can be done here as well. It's a partial answer. The exact answer I would have had if I could draw things. Yeah.
Okay, so I'll move on to the next question. Aditya asked that which computational approaches work best for proving into borophenes? Quantum mechanics, molecular mechanics, or a mixture of them?
No, I think it has to be quantum mechanics, because molecular mechanics works well for systems for which we could generate force fields. And usually force fields are known if we have highly established molecules which are studied well, and which can be studied with definite bonds that are well defined, like biopolymers, where only the hydrogen bonding has a difficulty, but otherwise one could have force fields that are quite well representing the structure. But in borophenes, especially 2 and 3 dimensional structures, we need to have quantum mechanical calculations, and the most commonly used method is density functional theory based on quantum mechanics, obviously. And if it is not, we don't generate the force fields that are good to use molecular mechanics. So I would say yes, molecular mechanics, maybe some more time later it might be applicable. I mean, we'll have good force fields to use molecular mechanics, but not now.
Someone asks that can we have boron analogues of biomolecules like lipids and carbohydrates?
Boron is available in biology, but always with 1 or 2 boron atoms. Boron is an essential element, but needed only in very small quantities. But interestingly, we can say that the way in which boron chemistry is expanding, especially the neutral boron equivalents that I mentioned. We have B12, H12, 2 minus. We could have C2, B10, H12, and these days there is what is called the boron neutron capture therapy for cancer. What it means is that if you can generate enough boron 11B at a particular point within the body, and you could shine very low energy neutrons, then you have a nuclear reaction, essentially boron dissociating into lithium, and that would generate enough energy to destroy cells. This is being done in very special cases, but that's a totally different use. There are reactions involving 1 or 2 boron atoms in biology. not clusters. So as an answer to the question, probably not large number of boron clusters that could be there in biology.
Someone else asked that just as fullerene is used in drug delivery systems, can borophenes be used in a similar way? How effective shall this use be?
It is not borophenes that are already used. As I said, carbohydrates, which are neutral systems that are already being used as drug carriers, but they are not borophenes, they are three-dimensional structures. The two-dimensional borophene structures are still very highly reactive. It reacts with anything. I mean, the oxygen affinity with the boron is very high. It's like silicon wafer also. You know, silica is very stable because silicon oxygen bond energy is very high. Such is the case with boron oxygen bond energy. So boric acid, yes, it is often there in the face powder that we use because nothing can happen to it after it has become that. But borophene, highly reactive, far more so than graphene.
Another anonymous question that we have is, what do the terms aromatic or anti-aromatic mean in boron chemistry?
Well, in a similar sense, we use the term. For example, if I take B6H6 minus 2, which is stable, a three-dimensional structure, an octahedron. You know, I have here in the screen only C2B4, but even if it is B6H6 2 minus, it has the same structure. It requires this minus 2 charge. Now, what happens? Like in benzene, if you add more electrons, it becomes less stable. If you remove electrons, it becomes something else. Just the same way, we can make this anti-aromatic if you add more electrons, right? It becomes B6H6 minus 4, and it will not be stable in this structure. It opens up. And if you add enough, you get back to benzene, right? So these three-dimensional structures have its electron requirement just as in aromatic systems. So it is anti-aromatic if you add 2 more electrons to have this structure. It just reorganizes into something else. Just as this becomes anti-aromatic if you had only C6H6 plus 2 as a planar neutral structure, right? It is not aromatic, but the moment it becomes a pyramidal cation, it is aromatic again, including chemical shift that you can see of C13. So the rules are similar. Aromatic and anti-aromatic concepts are similar, except that a lot more studies are there in organic chemistry, a field of its own, that we need to get similar detailed understanding and experiments in boron chemistry.
Another anonymous question. Can you mention some computational methods which a UG second semester student should try to learn, considering that the student is going to take a chemistry major?
Well, I would say start with the Huckel for n plus 2 pi electron rule, how you got it. You know, a simple algorithm is available even in books like Qualitative Molecular Orbital Theory by Stuyvesant. You can key in this, in the old language for Tran and compute. It's just matrix diagonalization, and you get the linear combination of atomic orbitals method immediately, right? You get the eigenfunctions and eigenvalues of the pi system. If you are slightly more enterprising, you can try extended Huckel theory, a three-dimensional kind of LCA-MO theory, and again, the programs are there in the public domain. I'm talking about program steps are there, and you can actually key in onto a machine and compile and run. So or of course you can be more enterprising and get a program. It's all there in the domain. I would say one should try learning LCA or MO theory to begin with, instead of starting with the most advanced one, so that one understands the model and then goes further. So I would say start with any of the LCA or MO programs that are available. And the theory from standard quantum mechanics quantum chemistry books.
Sir, one last question. This question is unrelated to the lecture, but what is your take on education abroad versus education in India at the undergraduate level?
It's a very difficult question to answer because there are better and worse places, right? So there are institutions where you could go and do well, probably better, not a whole lot better, and there are institutions where you can go and not do so very well. But there is one defect in our system which is trying to be remedied in institutions like Indian Institute of Science or the ISERs or in some IITs now, and that is we compartmentalize people even at the end of +2 and say, okay, if you want to do science, you have to decide whether you want to do physics, chemistry, biology, mathematics, or geology, and so on already. It is true also in engineering. It tells you that, okay, you can do computer science if you have the good grade. Otherwise, you will get into mechanical engineering or electrical and so on. In other words, we are compartmentalizing our students right from the beginning. That disadvantage will not be there in many institutions abroad. In fact, we got into this, I don't know, 150 or years ago because that is how the British made it. They changed it 100 years ago. We are still holding on. When you join for BSc, it has to be botany with zoology and chemistry. You are joining for physics, it has to be with chemistry and mathematics, not with history, for example. That bottleneck we will get over if we go to another country, unfortunately. But our education policy now is trying to change it. The new one would possibly will give you freedom to take mathematics and music, and after 2 years decide, okay, you don't like either of it, but physics as the major and take maybe history. We are trying. I hope that is what will happen in the new education policy. There is enough opportunities to do it, but we need to have a little more courage to do it, in the sense that it will be almost like a educational revolution, because most teachers and most colleges do not like to accept that fact that given freedom, will they allow all students to take any course that they want. It requires a change in our attitude. That aspect alone, I would say, yes, you have a definite advantage going into a good university. But otherwise, one would be missing many advantages. I mean, I can tell you, for example, like the group that is there in the 4-year BS program here, you would rarely have a batch of this caliber in most universities in the West. You may not have. This is the best and brightest. So is the case if you are in one of the leading IITs for a 4-year degree.
Thank
but
you,
this
sir,
general, this general thing is missing. What can you do? This is something that we are trying hard, and I think the new education policy has all the abilities to do it. Whether it will be actually executed, I hope it will be.
Thank you, sir, for taking all the questions. I will pass it on to Nikita to communicate the vote of thanks.
Hi, I hope I'm audible.
Yes, Nikita, you're audible.
First of all, we would like to thank Professor E.D. Jemmis for taking the time out of his day to give us this extremely fascinating talk on the chemistry of boron, as well as the structural and electronic relations of compounds of carbon, and as well as its allotropes. And at the same time, I would also like to thank him for inspiring us to search for questions. In his life, he pursued some question which came to him in the first years of his undergraduate studies, and that is truly inspirational. As a second-year undergrad, I think I am going to keep searching for more questions, and I can say the same of the organizing committee, and I'm sure that it inspired the audience as well. We would also like to thank the Dean of the UG program of IISc, Professor Anil Kumar, for making this talk possible. We would like to thank Team Pravega for supporting us and helping us in the organization of this talk. And lastly, we would like to thank our audience. Thank you very much for attending this talk and we hope you enjoyed it. Do check out the Pravega website, pravega.org, because we have a bunch of other talks lined up, and the next one being The Search for Quantum Gravity by Professor Shiraj Minwala of TIFR Mumbai. As for elementary lectures, we will be back in a week or so on 19 September 5 p.m. Do join us. Professor Jyotishman Das Gupta will be talking to us about solar energy conversion technologies and the scientific bottlenecks associated with it. Till then, goodbye and take care.
Thank you.